Yes, and today we will give and the linear independence, linear combination. First of all, we will give the we will define the linear combination of any set in our space. It's okay. So here our space R to the n, R to the n. Take the any vector v here. It's okay. Our space is 1. Take the vector v in our space. So, and this vector is okay. A linear combination of sorry, sorry. And here, let's give the linear combination. First of all, definition of the linear combination. And take our space R to the n. V is a vector. We have, and also K vector, V1, V2, V1, V2, and Vk. It's okay. If our vector here, V, it's okay. V can be written in this form. What's the form? V is C1, V1, C2, V2, and CK, Vk. It's okay. If our vector can be written as this form, and then we can say that here V is a linear combination of vectors V1, V2, Vk. Here, but and the coefficient of and the vectors C1, C2, Ck are scalars and means, and here real numbers. It's okay, real numbers. And means, and take the R vector V is okay. If it is possible to generate this vector, it's okay by using the V1, V2, Vk, but here and it should be, and the V is the sum of Ci, Vi. It's okay, Ci, Vi. So V is a linear combination of the these vector V1, V2, Vk. To understand the under this one, let's give an example. It's okay. For example, take the space R to the 3, R space here, R to the 3, example. It's okay. And take the vector V, it's okay, 4, 7, 2, and V1 is 1, 2, minus 1, and V2 is 2, 3, 4. It's okay. And let V is this one. V1 this vector, and the last vector V2. And question, determine whether V is a linear combination of V1 and V2. It's okay, V1 and V2. So means how to check that V is a linear combination of vectors? You have to check that V can be written in this form. V is C1, V1 plus C2, V2. Here, and that is our aim. You have to find C1, C2 such that V is C1, V1, C2, V2. So, and the question is this one. It's okay. Determine whether V is a linear combination means find the C1, C2 such that V is this one. It's okay. This one. If there exists a C1, C2, yes, V is a linear combination. If does not exist a C1, C2, such and the coefficients, so, and V is not linear combination of vectors. It's okay. So, and let's start and this one right here, C1, V1. It's okay. V1 is this one. Use a different color. Write this part. It's okay. C1 V1 plus C2 V2 is V. Write this one. C1 and the V1 here 4, 4, 7, 2 plus C2 is 1, 2 minus 1 should be R vector. Sorry, this one is V2. 1, 2 minus 1, 2, 3, 4. Sorry, this one should be V. 4, 7, 2. It's okay. This one. V1, V2, V. It's okay. Our aim is to find the C1 and C2. So what does it mean under this equality and the C1, C2 scalar and this one scalar multiplication? We know scalar multiplication for a matrix and this one is a vector. We know that and also matrix and the scalar multiplication this one. So means C1 multiplied by all elements by C. C1 2 C1 minus C1. First one. The second one, scalar multiplication, apply this one, 2C2, 3C2, 4C2 should be right-hand side vectors 4, 7, 2. So what is the left side? Left side, the sum of vectors means sum of matrices, spatial matrices. So this one gives the vector C1 plus T2C2. And the second row, the sum of the corresponding entries minus C1 plus 4C2. This one should be, yes, right-hand side, 4, 7, 2 vector. This vector is equal to this one and means corresponding entries should be same. And this one should be 4, this one should be 7, this one should be 2. It's okay? So, and so this one gives a system, and the first entry gives the first equation. C1 plus 2C2 is 4, 2C1, 3C2 is 7. The next one, next entry gives the next and also last equation. It's okay. 4C2, 2. We obtained this one. What does it mean, this one? This one is a linear system. Linear system. And our aim here, let's come back, find the C1, C2 such that satisfy this one, this condition. It's okay? And we have this system means solve this system. It's okay? Let's solve this system because our aim is to find the coefficient C1 and C2. Let's solve the system. So our problem can be transformed to the this problem solution of the system. So how to solve any linear system? Right, we know and this one from the previous lectures and solve the system and how to solve. Write the augmented matrix, apply the elementary row operation, so we get the solution. So write the augmented matrix here. A, B is okay. The augmented matrix, yes. Right, and here be careful. And this one is a linear system. This linear system contains three equations and two unknown. It's okay, unknown. So first unknown gives the first unknown and the C1, and look at the coefficient of C1 gives the first column of the augmented matrix 1, 2 minus 1. And the second unknown C2, the coefficient of C2 2, 3, 4, and right hand side 4, 7, 2. So this one is C1, C2. So look at this one is row equivalent to, yes, our aim is to solve this system, but be careful here and look at this one. or use a different color will be better. Look at this coefficient matrix and augmented matrix, this one, because and the contains on the right sides. It's okay. Look at this one. What's the first column? First column, the coefficient of C1. Let's come back here and these. Look at this one. Coefficient of C1 is this vector V1. V1. Coefficient of C2, V2, and V2. So, and this one is, we can skip and this part, and so we can write under this system, and also, and it is possible to write this one. It's okay, automatically, because, and this one is V1, this one is V2, this one is right hand side. It's okay, and V because, it's okay. Any question? No question, okay. So use the elementary row operation to get the reduced row echelon form. So we have one leading one, and then to get 0 here, and so apply this operation, multiply by -2, apply this one, multiply by 1. 1, 2, 4, apply this operation, -2 plus 2, 0, -2, -4 plus 3, -1, -2 gives -8, -1. And apply the next operation, multiply by 1, 1 minus 1, 0, 2, 4, 6, 4 plus 2, 6, this one. So the next one, to get leading one in this position, so, and multiply by -1. Our aim is to get 0. It is easy to see that. Multiply by 6, add to the last row. Is row equivalent? Not equal, right? 1, 2, 4. And apply this operation. Multiply by -1, 0, 1, 1. And apply the 6. And so look at this one, the last row, 6 times second row. It's okay. So we obtain 0 row here. It's okay, this one. So, and this one is row echelon form. To get reduced row echelon form, multiply by -2, and so we obtain, yes, this one the same. Apply the operation, 0, 1, 1, -2, 2, 0, -2, 2. It's okay. So to get reduced row echelon form and write the corresponding equation. First row gives the first equation. C1 is equal to, and this one gives C2 is 1. Yes, we get and the coefficient. So if there exists our aim, let's come back our question. Find there exists C1, C2 such that this one. So we obtain, and this one gives this system. Our problem, can we transform this problem and solve this system, and means, and this system has a solution or not? If has a solution, yes, our vector is a linear combination of v1 v2. It's okay. And here we obtain c1 c2, and means, yes, and means thus we get a solution of the system. So therefore our vector v is a linear combination of v1 and v2. And what is this linear combination? V is C1 V1 plus C2 V2, and right here V is 2 C1, 2, because C1 is 2 V1 plus 1 V2. It's okay. And this one, linear combination of V1 V2 times this one, and means this one plus V2. It's okay. V2. And how to check that this one is true or not? Right here V1 and V2, and then our aim is to get V. Yes, it is true. It's okay? Yes, V is a linear combination of V1, V2. It's okay? Any question? Any question? No question, I hope. Okay. It's clear everything. Yes, let's come back. This is the solution. Let's give this definition and take the any set here. It's okay. S is a set contains any k vector v1, v2, vk. It's okay. This one is a subset of and the subspace. It's okay. And here our space Rn. Our subspace, for example, this one, it's okay. V is a subspace. And take this set. This set is a set of vectors in subspace and means it's a subset of V. And take this one, different. This one is S. And this one, V1, contains this vector, VK. It's okay. So, here, V spans V or V is spanned by S if every vector in V, for example, take this one here and the vector V, it's okay, vector V, and is a linear combination of the vectors in S and means, and take this vector, it's okay, this vector V, and this vector can be written in this form, V1, C1 V1 plus C2 V2 plus CK VK, and then we obtain the vector V, and so, sorry, any question? Sorry, any question? Okay, no question. Okay. V is a vector in V. It's okay. V is a vector in V, and but not take to this notation because and the space is V and this one. Take the U, for example, U vector U here. It's okay. And if every vector in V, maybe here, it's okay, maybe here. So U is you have to check that U is a linear combination of V1, V2, Vk. Then and this set S spans V and means this S is okay generates the all subspace V. It's okay. Every vector in V, and it is possible to generate it by using the vectors in S, then this set S spans our vector space V. It's okay. Because every vector generates by using the V1, V2, Vk, but generates here, and every vector is a linear combination of vectors in S. It's okay in S. So let's give example to understand this concept. It's okay, this one. This one is important because you have to write the all vector in V, it is not possible infinitely many vector in V, but if we know this subset S and also S spans our vector space, so if we know the S and then it is possible to generate the all vector in V. It's okay. So we can generate by using the linear combination, of course, here. It's okay? So let's give an example. And S here contains 3 vector and v1, v2, v3. It's okay. Let's and in our example, S is contains v1, v2, v3. It's okay. We have only 3 vector in S. It's okay. This one. So determine whether S spans R cube, not in the subspace and the R space not Rn, R cube here, and check that R set S generates in the spans R space R cube. It's okay. R cube, not subspace. We know that R cube is a subspace of R cube itself. It's okay. So, and our aim is to check that this one. So, how to check that? You have take the arbitrary vector here. For example, take this vector, and you have to check the all vectors in R cube. It can be written as a linear combination of and the v1, v2, v3 or not, but not take the fixed arbitrary. Arbitrary means take the under this vector x1, x2, x3, not fixed and the entry. It's okay, components, arbitrary, because and the x1 may be 1, x2 0, 1, for example, 1 0 0, another one 0 0 0, another one 0 1 0. It's okay, but and it is not possible to check the every vector, but and here take the arbitrary vector x1 x2 x3. It's okay, and means x1 x2 x3 real numbers. It's okay, and so our aim is to check in this vector. It's okay, this vector can be written as a linear combination of v1 v2 v3. It's okay. So, and this set S spans R cube if we can find and the C1, C2, C3 and the constant such that C1 V1 plus C2 V2 plus C3 V3 X. It's okay. X R and R vector here. It's okay. R and the R space R cube. Take the arbitrary vector x1, x2, x3, and these denoted by x. It's okay. So S is v1, v2, v3. It's okay. This one. So and means this one is S. X vector is a linear combination of v1, v2, v3 or not. And means you have to find the C1, C2, C3. It's okay? So right here, and this equality, C1, V1. V1 is in here, and 1, 2, 1. Let's come back here. It's okay? And the V1, this one, V2, V3. C1, V1, C2, V2, C3, V3, and right here, plus C2, V2, 210 plus C3, 011 should be X. It's okay? So this one gives, apply the scalar multiplication and sum of the vectors. So we obtain one matrix, and so which one? Yes, C1 plus 2C2, 2C1 plus C2 plus C3, and the next one C1. This one gives, sorry, wait please. Sorry. And this one gives the C1 plus 0 plus C3. C3 is right hand side X. It's okay, X. x1, x2, x3. It's okay? So this one gives the system. Which one? And use and this one. First entry will be first entry. And second entry should be x2. The last entry should be x3. So we obtain this system, corresponding system. It's okay? So, and they solve this system because our aim is to find the C1, C2, C3. It's okay. So, yes, solve this system. How to solve? Write the augmented matrix and coefficient of C1, V1, this one, V2, V3, and X. So right here, V1, V2, V3, and right hand sides. So our aim is to solve this system. How to solve? Write the augmented matrix. Apply the elementary row operation. So how to get 0 here, 1, multiply by -2, multiply -1. So we obtain 1, 0, 0. And the next one, so we know that, and this one is multiply -2, add to the second row, and -2x1 plus x2. It's okay? This one gives multiply by -1, right side, minus x1 plus x3. That's all. It's okay? So, to get 1 here, have to get multiply -1 over 3, and then we get 1 here. And the next one to get 0 here, have to get 0 and multiply by 2. And also to get 2 here, for example, it is easy, multiply by -2. And then we get, yes, 0, 1, 0 here, yes. To get 1 here, and then we get 0, 0. But first of all, it will be prepared before the first operation, and I think it will be easy to get and the 0 here, 0 here by using the 1 over 3. So first operation will be multiplied by 1, add to the second row, because 1 over 3 minus 1 over 3, to get his 0 here in this position, multiply by -2, we get 0, 0. This one is 1 over 3, and then we get 1 here, multiply by, yes, 3. It's okay? So we get, and the C1 is this one, C2 is this one, C3 is 3 times this one. It's okay? We get the solution. We get solution, and means our system has a solution. Our system has a solution. Yes, it is possible to get the C1, C2, C3, and also, and the value of, and for example, look at the C1 and the R vector, arbitrary vector, x1, x2, x3, and the C1 depends on components of x. This one, and this one. C2 depends on x1, x2, x3, as C3 depends on the entries of x. So change the, for example, what does it mean in this one? Take the arbitrary vector in space here. We don't know and the components, and this one is R3. Take the x1, x2, x3. Our solution depends on the R vector. For example, our aim is to generate 1, 0, 0. So here, substitute here, x1 is 1, this one is 0, 0. This one is 1, 0, 0, 0, 0, 1. So we obtain, what's the C1? C1 is 1, C2 is 1, C3 is 1 to generate the 1, 0, 0. It's okay? So 1, 0, 0 and 1 times V1 plus V2 plus V3. It's okay? Look at this one. This one is V1. This one is V2, V3, V3. It's okay. C1 and this one, how to generate? Right here and 1, 1, 1. It's okay. And sorry. Depends on, and here C1, but this one is not true. What's the, and then here, sorry, this one, yes, what's the reason? And we get contradiction because, and they take the C1, 1, 1, 1, it is not equal this one. But be careful, this one is 1, x1 is 1, minus 1, should be minus 1. It's okay? And let's come back. Yes, now this one is equal. Right here, minus 1, C1, 1, 0. So we obtain, yes, minus 1, 1, 2, 0. So we obtain 1. Yes, x1. Right here, write the and this one. Our aim is to get minus v1 plus v2 plus v3 1, 0, 0. We claim that. It's okay. Right here, v1 is here 1, 2, 1 plus 2, 1, 0 plus v3 0, 1, 1. Our aim, we got 0, 1, 0, 0. Look at this one, minus 1 plus 2, the first row, yes. The second row, minus 2 plus 1 plus 1. This one gives minus 1, 0, sorry, 1. Yes, we get, sorry, 1, 0, 0. Yes, it's okay. But, and it is easy to see that, write another one. For example, this one, 0, 20. So, and right here, substitute here, this one. So, and we get the C1 and C2. It is possible to generate this one because our system has a solution. Solution depends on components of vectors. It's okay. So, and you don't have to check and this one, and our aim is to see that every vector is a linear combination of v1, v2, v3, and it's okay. So, and we obtain is a solution here. So means, yes, let's come back. So a solution of this system can be easily obtained for any choice of x1, x2, x3 because it's the solution depends on x1, x2, x3. What's the x1, x2, x3? Here are vector, arbitrary vector here. It's okay. So means every vector is a linear combination of v1, v2, v3, and means, and this set generates the all spans all space. It's okay. R space. It's okay. So we can say that S spans R cube. It's okay. R cube. Any question? Okay. Now another example here is okay. And S contains v1 v2, only two vector v1 and v2, v1 this vector, v2 this vector. Is okay. Determine whether S spans are cube or not. It's okay. Are cube or not. But be careful here, S contains only two vector and the same space are cube here. It's okay. Use a different color, will be appropriate. Take this one, R space R cube. It's okay, R cube. And the S contains only two vector, V1, V2. And here, as this one, our aim is to check that S spans R space or not. It's okay, not. So means, and what does it mean? Take the arbitrary vector here, not fixed. So, and any vector can be written in this form, x1, because R space R cube, and means every vector contains three components, x1, first component, x2, x3. It's okay? Check this vector, this one is x, vector x. It's okay, this vector. Our aim is to show that x can be written as a linear combination of v1, v2 or not. It's okay. So means find the constant c1 and c2 such that c1 v1, c2 v2 is equal x. It's okay, x. So what does it mean, this one? And means right here we obtain the system. This one gives a linear system. So unknown c1, c2, and the equation, three equation, because has a three components. And right here c1, c2, coefficient of c1, coefficient of c1, v1. Write v1 here, 1, 2, 1. It's okay, this one. And the coefficient of v2. Coefficient of C2 is V2, and right here 1, 1, 1, and right hand side x is this one, x1, x2, x3. So means solve this system, and this problem gives us a problem and the solution of the linear system. What's the linear system here? Linear system, this one. This one is a linear system, right? So our problem here, solve this system and they check that this system has a solution or not. It's okay. Write the augmented matrix here. So apply the sum operation to get reduced row echelon form, and our reduced row echelon form, this one. So what can you say about this solution? It's okay, reduced row echelon form. So, and if we obtain this one, this one is reduced to echelon form? Yes. So, what can you say about the solution? Look at the last, be careful, look at the last row here. 0, 0, 0 is equal x3 minus x1. This one is C1, coefficient of C1, C2. So, the last row means 0 times C1, 0 times C2 is equal x3 minus x1. This one gives 0, x3 minus x1. So, but what is the x1 and x3? x1 and x3 components of x, and these x arbitrary vector, not fixed. So we know that maybe this one it's not 0. For example, take the this vector 0, 0, 1. For example, take this one is our arbitrary vector in here, 0, 0, 1. Use a different color, maybe it will be appropriate to see that. Red 1. Take this vector 0, 0, 1 in R cube. Yes, any vector. So it is possible to get the linear combination of v1, v2. Look at this one. This one is x1 is 0, x2 is 0, x3 is 1. Take this one right here, and the 1 minus 0 is 1. Is not 0. We get contradiction because 0 is not 1. So means this and this vector 0, 0, 0, 1 vector is a not linear combination of v1, v2, and means it is not possible to generate this vector by using the S. So means what does it mean? As this set does not span our space because this one generates the sum vector in our cube. Some of them it is not possible to get the sum vector in our cube by using the S. It's okay. So our set does not span our cube. Let's come back because what is the reason? And we must then find the constant for any choice of the x1 and x3. Is okay? So, and here, and this system has no solution. It's okay? Yeah, and this system has a solution only if x3 minus x1 is 0. For example, and it means if, and take this and for example, how to check that? Take the R space here, R cube, and the V1 here, V2 here, R S set. And take this one, 0, 0, 1. It is not possible to generate by using the V1, V2. But take this vector, for example, x3 minus x1 is 0. 1, 0, 1. Yes, generated. It is possible to generate using this one because and the take and x3 is 1, x1 is 1, and then x3 minus x1 is 0. So and the right hand side and this one 0 is equal 0. It's okay. This system has a solution only x3 minus x1 is 0 means and the sum vectors it is generated by v1 v2, otherwise not. So this set does not span R cube. But here be careful, look at the previous example look at this one and sorry, this example, look at this one. Look at this one, and the same space R cube in this example and also R cube, and they take the arbitrary vector, but then the design is we know that, and the S spans R cube contains 3 vectors, and these vectors generates the R space. It's okay. This one generates all of them. It's okay. But here and the second one the same and the space, but take only v1 and v2. It is not possible to generate some of them, but some vector here, for example 0, 0, 1, it is not possible to generate 0, 0, 1 because 0, 0, 1 is not linear combination of v1 and v2. It's okay. Be careful. Any question? Any question here? No question. Okay. So, and another concept. Take the any set here. S contains k vector. It's okay. v1, v2, vk. And this set contains distinct vector in a subspace V of Rn. It's okay. And means, and here Rn Rn. Take the subspace V, subspace. Take the any subset here, S. S contains K vector. It's okay, K vector. So, and this set is a linearly dependent or independent. We can say that S is linearly dependent set if we can find the C1, C2, Ck and not all of them 0, such that C1, V1, C2, V2 plus C and here K should be K, Vk. Ck, Vk is 0. It's okay. So, and means look at this equation. This equation. Our aim is to find the C1, C2, Ck. It's okay. It is possible to get the non-zero solution of this one because this one gives the system. But this system, right hand side 0 means this one gives the homogeneous system. So means if construct this homogeneous system and look at this system, we know that homogeneous system. What can you say about the homogeneous system? And from the previous lectures, it's okay. We know and they take the any homogeneous system. And what can you say about the solution of this system? We know that, and maybe this system has only one solution, unique solution, only one solution, and means unique solution. And we know that an x is 0 is a solution always because a times 0 is 0. So this one is always solution. So, and the next one, and the next case, maybe this system has infinitely many solutions. We have two cases. We know that, and the x is 0 always solution, and the question is determine whether this system has non-trivial. This one is called trivial solution. And our question is, our homogeneous system has non-trivial solution or not? It's okay. If our system has non-trivial solution and means, and the trivial solution means C1 0, C2 0, Ck 0, always solution. We get this one is the unique solution, and we can say that, and the linearly independent. It's okay. C1, C2, Ck is 0 only, and the unique solution. So this one is called the linearly independent. If we get the has infinitely many solution, means it is possible to get the non-zero C1, C2, Ck, all of them not 0. So, and this set linearly dependent. It's okay? Linearly dependent. Any question? And we have one set here. It's okay. One set here, S. And V1, V2, and Vk. And our aim is to check that this set, Rn, R space, is a linearly independent or not. This one, how to check that? And construct this one. Ck, Vk is 0. Our aim is to solve this system, homogeneous system. And you have to check that this system has a 0 solution on the unique solution or not. If we get unique solution means we know that x is 0 only solution. It's okay, unique solution. So linearly independent set. S is a linearly independent set. If we get infinitely many solutions, other case, this one homogeneous system. This one is homogeneous system. It's okay. So infinitely many solutions. So means S is linearly dependent. It's okay, linearly dependent. So to understand then this one, let's give an example. It's okay, let's give an example. Yes. Look at this one. Consider these vectors v1, v2, v3 and determine whether S contains v1, v2, v3 linearly dependent or independent. So means write the equation. Which one? C1 and let C1 v1, C2 v2, C3 v3 is 0. It's okay. Start with this one. This one gives and the system because what's the reason? And C1 v1 1 2 0 1 plus C2 right 0 1 1 2 plus C3 yes 1 1 minus 1 1 should be 0 and the 0 means 0 vector 0 0 0. It's okay, 0 vector. So this one is applied and this one is scalar multiplication and then sum of the vectors. So we obtain yes C1 plus C3 and this one C1 plus C2 plus C3. The next one, this one should be 0 0 0. So first entry should be first entry. We obtain this one. This one gives this second one and the next entry gives the next equation. Last entry gives the last equation. It's okay. So we obtained this system. It's okay. So what can you say about this system? It's okay. This system, look at this one, contains 4 equations and 3 unknown. It's okay. So right hand side 0 and this one homogeneous system. We get homogeneous system and means and here our problem can be transformed into this problem solution of the homogeneous system. And we know that 0 always solution of the system because homogeneous. C1, C2, C3, 0 always solution. But our aim is to check that this system has non-trivial solution or not. It's okay. So how to solve this system? Write the augmented matrix, and here augmented matrix. Apply the elementary row operation. For example, to get 0 here, multiply minus 2. To get 0 here, multiply by minus 1. And then we obtain the next matrix. And to get 0 here, multiply by minus 1, multiply by minus 2. It's okay? So we obtain the next matrix. So, and to get 1 here, multiply by 1 over 2. So we, and also interchange this row because 0 row has a 0 row and this one is okay. So we obtain reduced row echelon form this one. So what's this one? And look at the last matrix. Augmented matrix C1, C2, C3. So first one gives C1 is 0. The second one C2 0. The next third row gives C3 is 0. It's okay. So we get only one solution. This one is trivial solution. We get only trivial solution. It's okay. Only trivial solution. So and means S is linearly independent. Linearly independent. So linearly independent and also means this one is V1, this one is V2, V3. R space here R to the 4 because, sorry, every vector contains and the 3 components. It's okay. Sorry, there's some problem. And here R space is R to the 4. S contains and the 3 vector here, V1, V2, V3, as this one. R space R to the 4 because every vector here and the 4 component. It's okay. So R space R to the 4. So S and it contains V1, V2, V3, and we get only trivial solution. So linearly independent. S is linearly independent. What does it mean? S is linearly independent. So and each vector in S, for example, choose the V2. V2, it is possible to generate V2 while using the V1 and V3. For example, C1 plus C2. It is not possible. It's okay because linearly independent vectors, and it choose the one of them, and the other by using the other vector, it is not possible to generate this vector. So, and linearly independent is set. It's okay, linearly independent. Any question here? Our example. No question. Okay. And here, let's give one more example, but I think it will be better. And let's have a break. It's okay, 10 minutes now.